since I'm not as late as I thought I would be, we'll actually have time to discuss a little bit the question that I mentioned the very first day, which is non-exchangeable systems. And the prototype now of a non-exchangeable system is the following. But what did I do here? I killed the 1/n. I replaced it by weights of interactions between the particles. If I want to stay within the mean field scaling, right, there are two relatively natural assumptions that I can make on those weights. And the first is that the total interaction on any object, on any particle, should be finite. Be negative, so I'm going to be careful. Same logic that what I had when I had put the 1/n. The second assumption is if I want law of large number to actually take place within that business, then I should not have strong interaction between any pair of particles. Individual coefficients, however, should be small, equivalent of my mean field scaling. You'll have a law, right? So, no, but this I can answer easily. Okay, you have a law of large number. All right. So, what's the size of the fluctuation in a law of large number when you have coefficients like this? Square root of the maximum coefficient. Right? So choose them as large as you want. If you choose them large, right, then you'll have more fluctuations, you'll have more correlations. If you choose them smaller, you'll have less. Right?
Maybe a different way of asking this is maybe this, presumably you're going to take n to infinity still, right?
Yes.
So if you put W super n, like put a set of weights there, yeah. Now, like, what can you tolerate?
Yeah.
This
but,
norm over. Yeah, that's
yeah. All right. But okay.
We don't know any symmetry, so I can have one of them be. I can have one of them be whatever.
I'll give example now, and you'll see what we're thinking of here, right? Now I won't give you a proof of the whole thing here because now that would be very technical. But I'll explain a little bit what are the main ideas behind that business. And first, so I'm going to argue that this is the right model for the physical point of view. In the sense that everything that we are doing with exchangeable systems, if you have in a lot of physical situations, that doesn't make a lot of sense. So if I have point masses and they interact, there's no particular reason why all my point masses should be equal. Unless you're doing dark matter cosmology calculations, and you believe all dark matter particles have the same mass, right? No one has ever seen one. You know,
we already sort of discussed that, but I don't fully.
You still disagree.
This argument, we could decide it's a reasonable model to postulate that the masses are random and that exchangeability will be preserved in this case.
Right, but you need to give me the time to go to this.
Right.
Shut up. So the first example, right, I'm going to take a gravitational interaction with point masses. And then we would have something like this. The question comes later because your question refers not to whether I should take this system or not, right? I'm at the level of a model here. I'm not going to discuss in the next minute how we approach those, right? So I'm not saying that the techniques we had before are not applicable.
Okay, okay.
Right? I'm just saying if you look at the dynamics of point masses, it doesn't make a lot of sense to just presume that they are all the same. So this is the first canonical example of a case like that, right? And you see, so first of all, the Wij are not symmetric. Even in basic physical situations in general, they are not symmetric. You think that the force between two mass is symmetric, right? But it's the acceleration that counts, not the force. And now my mean field assumptions here become very, very natural. I'm just asking that the total mass be of order 1 and that any individual mass be small.
I'm a little bit confused. If you have 1/n that converges, if you replace by 1/√ n, how could that give you the same convergence?
Let me, that was not in the plan, so I'm going to lose 5 minutes, but maybe that will be worth it. Let me do a law of large number But instead of an arithmetic average with equal weight, let me do a law of large number with any weight. Okay? So let's take xi that are IID, right, with 0 average. And I want to control the fluctuation in something like the sum over I of, well, let's call mi xi. Right? Sum of mi is equal to 1. Okay. So let's do this. So as usual, right, I picked to make my life simple, right? So I don't need to subtract any expectation. So you just calculate the square of this. So if I is different from j, right, this is 0. So this is the sum of I of mi square, the expected value of xi square, right, which we'll assume is finite. This is less than c, the sum over I of mi square. And if I use the fact that the sum is 1, then this is less than the soup of I over mi. My two assumptions come very, very naturally when you're trying to do something like this. And like this is controlling the size of the fluctuation. And this is just making sure that we have terms of order 1. And again, in that context, right, that makes total sense. So if you want to look at the solar system, right, you obviously have a problem here, which is the mass of the sun and of some of the larger planets. But if you're looking at all the rest, right, this is a very reasonable set of assumptions. Another big example, however, comes when you're looking out of physics. And now your particles, you're thinking of them are as agents on a graph. Right? And so they interact through this network. And there are tons of applications like this, right? From epidemiology to you know, machine learning nowadays, I imagine, right? To the actual structure of your brain. Right? So the other example is now I have a graph, right? It's a weighted directed graph. And you have two actually, right? So this is like that, and this is I and this is J, right? Then this gives you actually WJI, right? That's the effect that I has over J. And now you can have a very complex fixed, in that case so far, network of interaction. And a very, very important case, if you're thinking it that way, contrary to here, is that there you do not expect to have many interactions between them. You expect the graph to be sparse. In general, if I'm looking at an epidemiology model, right, people are not in contact with everybody else in the population. You are actually in contact with more than one individual, I mean, except during lockdown, if you're stuck at home, right? But in all other cases, you are in contact, right, with quite a few people. But that's not the population of Canada, right? And in your brain, right, you have around 100 billion neurons. And the average number of connections per neuron is of the order of a few thousand. So you have naturally sparse interactions. For example, I can play with scales. I can say that there is another scale within the graph. I can say that for any j, there is a total number or for any I, total number of j of order n theta, right? Such that wij is then of order 1 over n theta for any theta. And any such network will satisfy my assumptions. So in any such case, we have good reason to believe that we should be in a mean field scaling. Because the law of large number should still apply, and we should still see some sort of average field. Actually, a lot of examples of stuff like that. And now the first question becomes, how different are they from a technical point of view? And now I'm coming back to you. How different are they from a technical point of view from the approaches that I showed you or from other approaches that we know. And in that case, it turns out that if you look at the right empirical measure, then it still satisfies the right equation. To look at Wij, which is equal to Mj. I'm going to define an empirical measure that I'm going to call nu n. And nu n is going to be the sum over j of Mj delta of x. It still satisfies the right equation because when I'm taking the time derivative of this, right, I have an mi multiplied by this. So this actually symmetrizes the interaction. It would actually be the same thing if I was doing a fluid and then vortices, and each vortex has its own vorticity. I would have a corresponding equation, and that would be the right object. Right? And in the case of a fluid, that's maybe even more obvious because, yeah, that's what should give you at the limit the total vorticity in the fluid. How easy is it in trajectorial approaches to change nu n into nu n? That's my favorite answer this week. Depends. Because you lose things. This is not anymore a probability measure in general. The problem is not the total mass, because the total mass you could rescale, right? The problem is that if you're doing vorticity, those could have different signs. The things that now with vorticity, right, would be very natural to do for exchangeable system, but are just going to become more painful because you lose the nice signs that you had everywhere. Right? This will not have an energy with a sign, for example. I haven't had the time to talk about modulated energy technique, even though they are super important, but very obviously this is going to create problems. But what about the entropy? I have to distinguish between two cases. And the first case is when Mj are random and IID. Very natural approach in a system like that then becomes to try to say, well, this is just one extra variable, which doesn't move. It's okay if they are all of the same order. So as long as the corresponding moments are bounded, you see that here, if I'm in a case like that, right, to satisfy my mean field assumptions, I need that essentially they are all of order 1 over n. Otherwise, I will blow things up. Maybe not strictly, right? You can still have tails, and then you would need to wonder how bad the tails are, and then everything like this. Then add Mj to Xj as some, X tilde J, right? Keep doing what you were doing. You rescale them. You put the 1 over n in front of everything, and now you feel like you are pretty much back to the classical case of exchangeable system. Because here I can write things as dxi is equal to 1 over n, the sum over j of n mj k of xi minus xj. This is just part of your vector state. So in a case like that, there's a lot of reason to believe that you can extend the entropy approach in a relatively nice manner. What if they are fixed? Trouble. If they are fixed, now I cannot include them in the state, because if I include them in the state for the entropy, then I blow up the entropy. I'm putting Dirac masses in my initial condition. And now the problem is Hn, Fn, right, of nu n, and not the law of the right empirical measure that you would like to consider, which is this nu n. Stuff will start to break down. You cannot write a nice PDE over something that would be another joint law that would be the law of nu n. It doesn't exist. But it still doesn't break down everything, even in that case. If you have viscosity, right, so if you the sigma n don't vanish, you can actually still apply the relative entropy method because you're going to use the notes. There's a result by Winter about the derivation of 2D incompressible Navier-Stokes with positive and negative vorticity. to the Navier-Stokes, right? So with non-vanishing noise, not to the. So you really are in a case-by-case basis, right? As you can see from this very superficial description, that when you have a method, whether a method will keep working or not, is you need to check. So it doesn't break everything. It breaks some things. And you might still have enough to work with. What about the case where, you know, Wij do not have any simple structure, and I cannot define an empirical measure anymore. Not like that, not easily. The one approach that makes sense, however, is still to try to incorporate this within the state. So a relatively natural question here is to say, can I write that Wij is some W of psi I minus psi I psi j for some distribution of psi I that you make up and for some kernel W that you make up? You can do this, we're back to a sort of normal mean field approach. How bad it is will now entirely depend on how much regularity you have on this W. And Xi is a variable that you make up, right? You have to give me the psi I, you have to give me a W such that this holds.
So for instance, if I choose different classes of particles,
yeah,
that would fit.
That would fit perfectly, right? But in general, it's going to be a lot more complicated. And here, then, what I would have is a bit of a weird system at the limit. I would now try to solve the mean field limit, right? Which I have added a Xi variable. This is weird because you're not given the initial data, right? And then you're not interested in actually knowing F bar, right? That F bar, you're interested only in knowing the average of F bar inside. This is what is going to be, if everything goes well, this is what is going to be the limit of the empirical measure. And now if I'm thinking of the difference between mu n, and all of that in that context, right, you see that what that would mean is I would take different moments of F bar to get all the various versions of the empirical measure that might show up in the analysis. I can fit essentially everything that we discussed so far within this framework, but this is weird. This puts you into something that is called graphon theory. And graphons were something that were very famously in the early, from 2000 to 2010, right? They were introduced, in particular by Lovash, to represent the large-scale limits of some graph, random or deterministic. Okay? And if I'm going in this direction, okay, and now I'm trying to be a lot less ambitious, so we are going to go back to the case where K is Lipschitz. And let's assume that all Wij are of order 1/n. So I'm going to do the deterministic case, right? I'm going to fix them, but now I'm going to take the case of a dense graph. When you open Lovash, and Lovash will tell you the following. Exists psi I in the interval 0, 1. There exists a kernel W in L infinity of 0, 1 square. And now I can build, so I started the wrong way. Build the following kernel here. So build Wn by taking it piecewise constant, right? So you take the square, 0, 1, 1, you cut it into n piece in every direction. And then in here, which corresponds to piece I and piece j, you put it piecewise constant equal to Wij. Then up to a permutation of the indices, we will have a convergence of Wn after permutation to W. This is a big result, okay? So it's not something you can show in 2 minutes, but it's true. There exists a permutation. The question is, it converges in which norm? You need a strong norm, right? Such that, so let me call that Wn of the Wij. W minus Wn of W sigma I sigma j, right? So after permutation, this converges to 0. tends to infinity in the what is called the cut distance that you can relatively simply see as the norm of the kernel as an operator from L infinity to L1. It's not an LP norm, but it's not a weak norm. And a very remarkable fact is that this convergence is actually enough to do the mean field limit, where F bar solves the right equation, which is this guy. This is mostly due to Medvedev, right? And quite a few of his collaborators. It's actually not that hard to prove once you put everything all together. And that has naturally inspired a lot of interest because can you do this in general? Part of the problem here, of course, is if I want to use graphal theory, then I need that. Because you see that the way I'm defining this thing, right? The way I'm defining these things, right? If I want the result to be in L infinity, all of those objects need to be bounded. So in particular, this kind of results cannot apply. It can apply to sparse random graph, but that's a different story because then you do it a little bit differently. But here you need a dense graph, but you can still do it in a sparse graph, except now it becomes horrible. Now I don't have this very nice Lovash result that would solve my problem immediately. Logic here, the limiting kernel would be in L infinity of psi with value measured in zeta, because that corresponds to an L infinity norm with L1, right? Because that's really a sup of I of the sum over J. And if this is the only bound you have, that's the regularity you should expect at the limit. And those objects are nasty. You even have several ways of defining them. Because that's not a good space that reacts very well with something that has to be defined almost everywhere. We did it, and you do end up with something like that. And I'm not going to try to describe it too much, but I will say that there is a key aspect into this, which is to forget about F bar as much as possible. And the key idea is to look at proper moments of the solution. First step is to do a propagation of chaos. If K is Lipschitz, and that's the first interesting remark, this is easy. Propagation of chaos is easy and is done in the standard way using a trajectorial method that is still working very nicely. At this point, you think I'm done, right? But your particles are not IID anymore. They are just independent. What you have after propagation of chaos is a coupled system of PDE on the law of each particle. If I call Fi of Xi, what you get is something like dt of Fi plus divergence X of the sum over J of Wij K convolved with Fj Fi. And here you need to do something, right? So that's the first, I think already this is interesting to realize, right? That we are so very used to having propagation of chaos solve everything. And sometimes it does not. And sometimes it does not because you have more structure and you need to handle the extra structure. What would we like to know about this? Well, I would like to know, for example, the one particle distribution. Right. So I'm going to call that G1, which is just that. You can try to write an equation on G1, and then it involves a sort of two-particle distribution that is a correlation function weighted by the graph. And you can keep on going. And you end up writing a hierarchy of equation, but not the boring hierarchy that we had just handled, right? Hierarchy that is indexed by trees. That wouldn't be fun otherwise, right? So tree with just one node, you end up with this, right? A tree with two nodes, you have only one, so you have only one here, but afterwards you have several of them. Hierarchy you have, right? You still have the tensorized version with as many as you have of nodes in your tree. But then you have those weights that you have to put and that are done by multiplying over all the edges of the tree, the corresponding weights that you find from that edge. Then you have an equation like that, where I denote t plus I, the tree that you obtain, by adding one leaf at node number I. Now you start to scratch a little bit and understand what this does. This follows the successive interactions between particles. So I start with one particle. I want to calculate its time derivative, so I need to know which other particle it interacts with. So I get that and I pay with that weight. And in general, when I start building this chain of interaction, right, and I can have several chains, that's why I have a tree. Whenever I want to calculate the next one, well, I have to say we are at the limit, right? Propagation of chaos was done. So I'm going to pick another particle that I have not listed yet, and it's going to interact with this other particle, and so I have to add it to the tree at the correct location. If the system was exchangeable, right? If all those guys were identical, G of the tree, G of the tree would depend only on the order of the tree, of the number of nodes. And I would be back to the classical Vlasov hierarchy. So it's those objects that you study. And those objects are nice because they never figure explicitly the W. The W is in the initial data, and you put it there, and then you don't touch it anymore. And so getting convergence on this is easy, because you don't need to do anything special. You just need to make sure that the initial data are converging.
You're saying you're at the limits?
So I took propagation of chaos. So that's the first limit, and that gives me this coupled system of PDE instead of having a coupled system of SDE. And now I'm trying to take the next limit, right? That's for any n, and so I still have a piece of a limit n tends to infinity here, right? That's the tricky part of this. Is it really two limits that you're doing? You're taking the limit of zero correlation first, but then you still have a graph, so you still have to push the graph to infinity.
Find this before taking the graph?
Yes, but the formula are bad. But yes.
Can you study
And we are trying to do this before doing propagation of chaos in the hope that then we don't need Lipschitz kernel. But I haven't checked all the calculations yet, so I cannot say whether that would be working. But yes, you have an equivalent definition here before propagation of chaos.
And do you really need trees? I mean, that's an ordered growing graph.
You'll get all the trees here.
I mean, you don't have to have a tree, or I have an ordered growing graph that I was watching.
For this hierarchy?
Yeah.
But they only connect, if you start with a tree, this only gives you a tree. So you can sure start from anything you want, but making your life painful, right? You're just adding leaves. And so if you start from a point, you'll only generate trees like that. Be careful as well when you're defining. You also have to be careful with the initial data. If you're trying to apply this to something.
I guess what I was asking is, you have a model where you're building a type of tree. But I can also just reveal a graphs, an infinite graph slowly, right? Is it the same? If the initial one converges, then good.
Yeah, it's the same, right? It would be the same. Yeah, because absolutely. But you do have to be careful here because of the scaling. You cannot put any graph there, otherwise this is plus infinity. Right, so you need something that is carefully ordered so that you can, remember this is L infinity measure. So you need to make sure that you're only going to integrate once in the second variable for this to be bounded. So you need to do it a little bit carefully, but yeah, otherwise that would work identically. But the fun thing about this hierarchy is we can get uniqueness on it in exactly the way I showed you an hour ago. And propagate, so we propagated L2 norms, for example, that's the simplest. And it's the same thing, you have solved the extra derivative here, and it works exactly in the same manner. We have uniqueness, and so this is the key tool that allows to bypass a lot of technical craziness that you would have to face otherwise when trying to extend graphons to this kind of measure space. And people have tried to extend graphones to measure space. You have papers, but it's very cumbersome. I think it's because you need the right topology. It might be that there is another way of defining the right topology on the extended graphones that we haven't found. This is the topology of convergence that we're using. Give you a bit of an idea of what can happen when you go to non-exchangeable system. And again, it's not completely different. So you don't feel like you're on another planet and you need to relearn everything, but there are enough differences that you do need some sort of other.
Well, we've had a lot of questions, but any more questions?
On this problem for sparse graphs, I think there was a paper a couple of years ago by probabilists studying this. And so they had this notion when you have large graphs of local convergence of rooted graphs and the trees showed up like that. And how is it related to your point of view? I mean, if
so this is not, this definition here is something very classical in graphon theory. Those are the moments of a graph. Lovash was using this a lot. So it's not something that we pulled out of our hat, right? This was well known as an important object into all of this. The new ingredient in what we are doing is I think, the uniqueness of that and the way we use this to define the topology of convergence on the system, right? On the coupled PDE system. Because using this to define the topology of convergence on the graph was also very good. And you can show in particular in the standard theory of graphon, you can show that convergence of this is essentially equivalent to the cut distance.
Still need that the supremum of the wij goes to 0?
Yes.
So maybe it does not apply to the sparse graph, right? Because
it depends how sparse your graph is.
I think what he had in mind was really locally your bounded degree.
Yes.
Ah, sorry. So, but that's not a question of bounded degree. You mean you only interact with a finite number of objects? Yeah, that I have no idea how to do. And yeah, now I see the paper that you're referring to. Yeah, I would love to be able to put a dynamics into this. And I have zero idea how to do that.
I have another dumb question. I think it's similar to the one I asked you at lunch, but I'm still having trouble wrapping my mind around it. So if you, like, let's say you're talking about the galaxy,
yes,
or something like this. So if you tell me, okay, I'm going to treat all the particles as stars, and I'm going to distribute the masses in some kind of IID way,
yes,
and then I can take a mean field limit, I'm going to get a galaxy. This makes sense
yes.
to me. Does that work? So that should work, right?
That should work, yes.
But now you say,
at least on some timescales.
Yeah, yeah. But then like, okay, then you're like, all right, what if I'm going to add in the planets? So then I've you know, it seems like, okay, I have two species that are well separated. It seems like, okay, maybe I could do something similar to what you're saying, but, you know, making a special case of treating the stars and the planets separately, yes, and stuff like that. But the mean field limit doesn't seem to make sense anymore, right? Because like the planets are all stuck around the stars and stuff. Like, how does it work?
It's still a mean field limit.
It is.
Yes. But right. Because there are two questions in what you're asking. Mm-hmm. The first question is, how does it make sense if you have very different objects, but you would still have a mean field limit in general?
In general, yeah. I mean, I can come up with other examples where it seems clear that it's okay.
And I think this answers it. And what you have really is you still have propagation of chaos, and you can still see an average field. The mean field limit is at large scale. If you're looking at it at the scale of a galaxy, you're not looking at what's happening independently in a given solar system.
Right. So you,
if you try to zoom in the mean field limit, you don't have a mean field limit anymore.
Right. So the mean field limit doesn't see that the planets, that each star is circled by some planets. No. It doesn't see that that's too small scale. Right. But you can still take the limit. It's totally fine.
So that's the first part of your question. But there's a second part, which is specifically with gravitational system. Mm-hmm. And that has worried people for a long time, which is that precisely you can have this configuration where you have several particles around, and it's like a fixed configuration and they don't go away.
Yeah.
And how on earth are you going to be able to handle that in your proof of the mean field limit?
Yeah, it seems tricky. Yeah, exactly. Yeah.
And whether this kind of configuration then could break the correlation and propagation of chaos. But that's something that is very specific to having a singular attractive force Hamiltonian that will build this kind of periodic setup at small scales.
Presumably, if your W's had some multi-scale structure,
Yes.
you would be perfectly fine having a mean field limit, like
Yes.
to a graphon reaction here and there, and then those themselves interacting
Yes.
to give the bigger limit.
And all of this will be very nicely handled by this crazy limiting kernel, which is L infinity with value measure.
So now you know the big scale limit is true, and you know all the mesoscopic limits. But can you then talk about how can you get the equation for the mesoscopic?
Let me show you an example of W at the limit.
So you get a mesoscopic dynamics with the coupled equations.
You can even do something where the scales are not separated. Here's an example of W. Okay. For any phi that is measure preserving. What this tells you is that you sort of have layers, right, which are the level set of phi.
Yeah.
And then one layer is connected to another layer by repeatedly taking phi of the corresponding points, right? And so you have this crazy chain of interaction that might, be periodic if phi to some power is identity, or might never be periodic and then push things to scales all over the place. And you see this is L infinity with value measure, right? Sort of stuff that you have to be able to put.
Okay, so I think we should stop here. So we have another talk afterwards, but let's thank Pierre Emmanuel for